So in this module, we discuss the basics of cache memory, which include how the cache is organized and what happens when there is a miss, how to select a victim block in the cache, and what happens when we want to write a block to the cache. And also we look at the issues related to how to access the cache memory and so on. So before that, we start with an example why we actually require a cache memory. Consider a scenario where a system without a cache memory. So when processor wants to read the data which is stored at an address X in the memory, so it sends a request, a load request to the memory, and the memory supplies the data stored at address X. Let us assume that the data stored in that particular address is ABC. We know that memory access takes a lot of time, hundreds of cycles. So this operation will be very costly. And every time if you are going to the memory and spending hundreds of cycles, our overall performance will be degraded significantly. To minimize the performance penalty, what we can do is we can consider a faster memory between the processor and the main memory, which is called as a cache memory. We send the request from the processor to load the data which is stored at an address X. We first search in the cache, and the cache is initially empty, so there is no data. We will go to the memory and get the data. But because we are spending anyway hundreds of cycles to get the data from the memory, rather than reading only the required word of data, we read a collection of data items which are nearer to this address X. So we bring this chunk of data from the memory and store it in the cache memory, so that in the future, if processor requires any data in this particular chunk, the cache memory can service. So effectively, the cache memories improve the overall performance of the system. DRAM cell takes more time to access compared to an access from an SRAM cell. So that's the reason why typically cache memories are designed using SRAM technology. The DRAM memory density is much higher, where it typically takes one transistor and a capacitor for one bit of information compared to 4 to 10 transistors in the case of SRAM cache memory. So because of that reason, the size of the cache is also considered typically smaller. And another point is the access time of the cache also depends on the size of the cache. So if the bigger size cache is considered, then automatically it is going to take more amount of time to supply the data to the processor. Keeping all these reasons, typically we consider the cache memories of reasonable size compared to the size of the main memory. In addition to that, because the cache memory is typically placed on the chip, and the chip real estate is very costly, so we cannot dedicate too much space on the chip for this cache memories and so on. And because we are bringing a chunk of data from the memory, to minimize our number of accesses to the memory as long as cache supplies the data required by the processor. So what is the size of the block we have to consider? Typically we consider a block size either as 32 bytes or 64 bytes. If you consider a smaller block size, the applications may not exploit the spatial locality properly. At the same time, if the block size is very large, then the number of blocks stored in the cache memory is limited, and as a result, the overall conflict miss rate may increase. So that's the reason why typically the current processors are considering a block size of 32 bytes or 64 bytes. So having discussed why we require a cache memory, now we'll look into the organization of the cache memory. As I mentioned previously, so we bring a block of data from the main memory to the cache. So effectively, the data transfer happens at a block level granularity between these multiple levels of the caches or from the memory also. So effectively, we can view a cache as a collection of blocks, Now, how do we organize these blocks in the cache? There are three ways in which we can organize the cache memory. One is the set associative cache, where the total number of blocks are arranged in collection of sets, and each set is accommodating a fixed number of blocks. So, effectively a cache is divided into sets and the ways. In this particular example, we consider 4 sets and each set is accommodating 4 ways, and that is the reason why this is called as 4-way set associative cache. So, once we have this type of organization, now how do we map a cache block to a particular location in the cache? So, for that we use this mapping formula. Take the block address and apply mod operation with the number of sets in this cache. For example, if my block address is 20, and because here the number of sets is 4, so automatically this block address 20 is stored in set 0. And once we fix a particular set for a given block, within the set the block can be placed anywhere. Either we can place the block in way 0, way 1, way 2 or way 3. So, the advantage with this set associative cache is, if multiple blocks are mapped to the same set, still we can service the request by accommodating all these blocks in a particular set, as long as the number of blocks we accommodate is not more than the total number of ways of that particular cache. If we want to accommodate 5 blocks in a set, so we can at most accommodate 4. So, to insert the 5th block, we have to evict one of these existing 4 blocks. So, for that we use cache replacement policies that we discuss after a couple of whiles. So, having discussed the set associative cache, now we will concern 2 extremes of the set associative cache. The first one is, we restrict the number of ways per set. Let us assume that each set accommodates only one way. Now, in this particular example, we have 16 blocks which are arranged in 4 sets, and each set is having 4 ways. Now, when I restrict the number of ways per set to be 1, then automatically I am going to have total 16 sets, and each set is having only one way. Effectively, it can accommodate only one block per set. And this organization is called as direct mapped cache. So, in this direct mapped cache, to map a particular block to a particular location, a fixed location in the cache, all we have to do is we apply the mod operation on the block address with the total number of blocks in the cache. Again, in the previous example, if I want to store a block address 20 into this direct mapped cache, so 20 mod 16, because there are 16 blocks in the cache, so which is effectively we are going to store that at block 4. So, starting with block 0, block 1, block 2, block 3 and so on. So, we are going to put this the 20th block and block 4. So, compared to set associative cache, here because we have only one location per set, if application requires multiple blocks mapped to the same location, then we are going to get too many number of misses. So, it is actually not efficient in terms of the cache miss rate, but it is efficient in terms of the search time. If you want to locate a particular block, all we have to do is apply this mod operation and we will get the block directly. Whether the block is present or not, we will get the information. But whereas in the case of set associative caches, when we apply the mod operation, we just get only the set, and after getting the set, we have to search in that set. All the ways in the set we have to search to see whether our requested data is available in the cache or not. So, which is going to take slightly more time compared to the search time in the direct map cache. So, now we consider the other extreme, where we consider a single set in the cache, but this set can accommodate all the blocks of the cache. Again, considering this example where 16 blocks are there in the cache, and if I organize in a way where we consider only one set and this set is accommodating 16 blocks, then we are going to get the other organization which is called as fully associative cache. And this fully associative cache, the block can be placed anywhere, whether you can place that in the way 0 or way 1, way 2 or at the end. So anywhere you can place the block in the cache. So as a result, it will be efficient in terms of utilizing the cache space, but it is inefficient in terms of searching for a block, because when we keep a block anywhere and if you want to search for that block, we have to search all the blocks in the cache to know whether a block exists in the cache or not. So that's the reason why search time will be very complex in this particular case, and also it consumes significant energy as we have to search every location in the cache. But the current processors are typically using either direct map caches or set associative caches because of their advantages in terms of reducing the cache miss rate and simple search. So having discussed this cache organization, now we will see how to locate a block in the cache. As I mentioned earlier, the cache memory size is very small compared to the main memory size, and also the granularity at which the data transfer happens between the cache and the main memory is at the block level granularity. So multiple blocks of the memory can be mapped to a single location in the cache. So how do we locate a particular addressed block in the cache? So in this particular example, we considered a set associative cache, but this can be applied for direct map cache or fully associative cache. Having the address available from the processor, we can divide that address into 3 fields. LSB few bits are going to specify the block offset. Next few bits are going to specify the index, are also called as a set index. MSB remaining bits are going to specify the tag of that particular block. So having divided the given address into 3 fields, in the set associative cache, we use this set index bits to locate a particular set, and within that set we search all the blocks present in that set using the address generated by the processor with the addresses associated with the blocks present in that particular selected set. If there is a match, that indicates that our block is present in the set. If there is no match, then the cache is not having this particular requested data. In the case of direct map cache, because each set is storing only one way or one block of data, so effectively we are going to use both the tag and the index together, and that is called as a block address, and we apply mod operation on this block address with the total number of blocks present in the cache to locate the particular block. And similarly, in the case of fully associative cache also, because we can store anywhere, so we have to search entire cache with this block address to locate the requested block, whether it is present or not. So we mentioned that processor generates an address, take the address and use the tag bits, use the set index bits and go to a particular set and search for a particular block within that particular set. But to understand all these things, we actually need to understand how the actual cache operation happens inside the cache. So for that, we need to know the cache microarchitecture in detail. If you look at the cache microarchitecture, it consists of data array and the tag array. The actual data is stored in the data array, whereas the tag array stores the metadata associated with this data. The metadata consists of the tags, valid bit, the dirty bit and all other necessary information. And we also have a decoder which is called as a set decoder, and we have multiplexers, sense amplifiers, comparators, drivers, Now when a processor generates an address, we partition that address into 3 fields: tag, index and the block offset. We take the index bits and supply that to the set decoder, and set decoder will select one of the sets. Effectively, this output of the decoder is connected to the word lines in the cache, and based on the set index bits, one of the word lines will be activated, and also we activate the bit lines. The intersection of the word line and the bit line will give you an access to an SRAM cell which supply 1 bit of information. So when the word line is activated and all the bit lines are activated, we read the data from all the intersection points, and this data goes through the column access sense amplifiers. The sense amplifiers will ensure that no full voltage swing happens on these bit lines. So because once there is no full voltage swing happens, your dynamic energy consumption will be minimized. And once we read the data, we give the data whatever we read from the tag array to the comparator as one input, and the other input we supply from our processor generated address from the tag field. And if there is a match that indicates that our requested data is present in the cache, then we read the corresponding data from the data array. Finally, we read a block of data because our tag is actually associated with the cache block. Once we read the entire block, we have to supply the requested word to the processor, because the processor always requests word of data. It will not request the entire block of data. And remember, the block size is 64 bytes or 32 bytes, and processor may request 32 bits or 64 bits of data. So to select a particular word in the selected block, we apply block offset and then supply the requested word of data to the processor. So as a result, there are lots of a sequence of operations happen, starting from the processor generated the address all the way up to supplying the data to the processor. And in this, we can either perform reading from the tag array and data array in parallel, or we can perform the reading from the tag array first, followed by reading from the data array. So if I perform the operation parallelly in both the tag array and data array, then this is called as a parallel mode of access, which is efficient from the point of access latency, because our two operations are overlapped. So as a result, the overall access time will be the max of the tag array access time and the data array access time plus the access times associated with the other peripheral components in the cache memory. Though it is efficient from the access time point of view, because it is accessing all the ways in the cache, it is not efficient from the energy point of view. Consider a scenario. If the cache is having 4 ways per set, in other words, it is a 4-way set of cache. If we consider, we know that a requested block can present at most in 1 way in a set. So that indicates that when we are accessing a 4-way set of cache parallelly, we are reading 4 tag blocks, 4 data blocks simultaneously, and searching all these 4 tag blocks with the tag of the supplied address. And if at all, if there is a match, only 1 tag block is going to give the hit, so that effectively wastes the energy due to accessing the 3 data blocks. So from the energy point of view, parallel mode of access is not efficient, but from the access latency point of view, the parallel mode is efficient. So other alternative is, first access the tag array and compare tag given in the address with the tags available from the tag array reading, and if there is a hit, then only access the data array. If I do this, effectively I can minimize the access energy wastage due to accessing the other blocks in the data array. Though it saves the access energy from the access latency point of view, because these operations are serialized, and the overall access time is equal to the access times of the tag array access plus the access time of data array plus the access times of all other components in the cache, which actually increases the overall access time. Now, so where do we apply this parallel mode of access and where do we apply the serial mode of access? Typically, the caches which are very close to the processor require the data as fast as possible. In those cases, we apply parallel mode of access. And whereas the caches which are very far from the processor, we are actually applying 8-way associative or 16-way associative caches in those levels of the caches, where it is not necessary to access the tag and the data arrays parallelly. So, in such cases, we can apply a serial mode of access. In other words, typically for L1 cache, we can apply parallel mode of access, whereas for L2 and L3 caches, we can apply serial mode of access. So, now we discuss the cache miss classification. When a processor generates an address to read the data from a particular location in the cache may have the data or it may not have the data. If the data is not there in the cache, then we consider it as a cache miss. And these cache misses can be classified into 3 groups. The first one is called as the compulsory misses or cold misses. And these are the misses that happen for the very first access to a block. Initially the cache is empty. When a processor generates an address, you cannot find anything in the cache, we incur a miss because there is no data in the cache. And this miss is called as a compulsory miss. The number of compulsory misses is independent of the cache size. Even if you consider 32 KB cache, 64 KB cache or 128 KB cache, these compulsory misses will be the same. Only one way you can reduce this compulsory misses, and that is by increasing the block size. But remember, if you increase the block size, the total number of blocks stored in the cache will be reduced, and as a result, the application, especially in the case of data accesses, may not exploit the locality properly, and which in turn can increase the overall conflict miss rates. The second class of cache misses is the capacity miss. For example, consider a fully associative cache where we can keep a cache block anywhere in the cache. Now assume that a scenario where the entire fully associative cache is full with valid blocks of data. A processor requested a data which is not there in the cache. Now we need to bring in the new data from new block of data from the lower level of caches, and we supply that to the cache. But now this cache is full, so we evict some block from this fully associative cache and keep the new block into this particular location. And now after that, if processor requests a data to the previously evicted block, so we incur a miss. And this miss is happened because we were not able to keep that particular block in this cache due to the lack of space or lack of capacity. And this is called as the capacity miss. A miss occurs because there is no space in the cache. So one way to reduce the number of capacity misses is by increasing the cache size. Rather than considering 32 KB of cache, if I consider 64 KB of cache, my cache capacity is doubled. So as a result, the capacity misses can be reduced significantly. And the third class of cache misses is called as conflict misses. Consider a set associative cache where we know that the blocks are mapped to a particular set. Let us assume that processor generates an address which is mapped to the third set in this particular exampled set associative cache, and also assume that this set is having all valid blocks. Now the new data cannot be there in the cache and cache incurs a miss, and when we bring in the data from the lower level of the caches, we evict one of the blocks from this particular set and store this new block in that. And after that, if processor generates a request to the evicted block, we incur a miss. That miss is called as conflict miss. This says that block is not found in the cache because there is a conflict in the particular set, even though the other sets have empty spaces where a block can be placed, but because of the set associative property, blocks are always mapped to a particular set. So as a result, we incur a miss. This says that misses happen because of lack of space in a given set. That is called as conflict miss. To reduce the conflict miss rate, all we have to do is increase the associativity of the cache. Rather than considering a 4-way associative cache, if I consider 8-way associative cache, I can reduce the overall conflict miss rate. So among all these types of cache misses, the compulsory misses are having very low fraction of overall misses, whereas the conflict misses have the highest percentage of misses. So in other words, the conflict misses are predominant, and we have to optimize our caches such a way that the conflict miss rate is reduced to improve the overall performance. And when we consider direct mapped caches, we know that the search is simple, but the conflict miss rate is very high, because in the direct mapped cache, each set can accommodate only one block of space. On the other hand, fully associative caches, in which we can keep blocks anywhere in the cache, so which incurs very low conflict miss rate, but the search time is very high. And set associative caches reduces the conflict miss rate significantly compared to the direct mapped caches, and also it has low search time compared to fully associative caches, and because of all these advantages, typically set associative caches are predominantly used, followed by the direct map caches in the current processors. So when I say there is a miss in the cache, now we have to bring in new block of data from the lower level of the caches and keep that in particular cache. So but if I consider a set associative cache where a set will have multiple blocks, if it is a 4-way associative cache, set can accommodate 4 blocks. Out of these 4 blocks, which block to be evicted to make a room for the new block that is brought from the lower level of the caches or the memory. So to do that, we have to consider cache replacement policies. In the case of direct mapped caches, since each set accommodates only one block, there is no question of which block to be evicted, because only one location you have to evict that particular location and store the new block into that location. But whereas in the case of set associative caches, variety of techniques proposed in the literature, but in this discussion we are going to consider 3 policies, which are random replacement policy, least recently used policy, and pseudo least recently used policy. So consider set associative cache with 4 sets, and each set is having 4 ways, and also consider a cache block address reference pattern ABAC BDA, and all these addresses are mapped to the third set in the cache. And so when processor generates an address for A, we are keeping the corresponding block in the first way of the third set. When the processor requests the address location B, we are going to keep the block in the second way and will continue. And after the processor generates an address for D, then we keep D in the fourth way of the set, and the state of the set associative cache after referencing the address location D is like this, where the third set has 4 blocks with the data corresponding to A, B, C and D. When the processor generates an address for A again, because A is already there, so it supplies a data from the cache and it is treated as a hit. Now consider a scenario when a processor generates an address location E and that corresponding to a particular block. Now how do we store? So if I consider random replacement policy, because the block which consists of address location E is not there in the current cache, so we have to evict one of these 4 blocks, and when we want to evict, so if I consider a random replacement policy, we can pick a block at random by generating a pseudo random number, and in this particular case we consider the first block is evicted and the block containing the address E is stored in this particular location. If I consider least recently used policy, I always select a cache block which is least recently used in the past. So among all these blocks, so block containing the address C is least recently used and we evict that particular block and keep the block containing the address E into that. Mainly the least recently used policy is working on a principle that if a block is not accessed recently in the past, there is a high chance that block will not be accessed in the near future also. So with that principle, LRU policy is designed and it always selects a block which is not recently accessed in the past. But how do we count the time? How do we know which block is not least recently accessed or which block is recently accessed? To do that, we associate a log n bit saturation counter for each of the blocks where n is the associativity of the cache. In this particular example, we consider a 4-way set associative cache. So we consider a 2-bit saturation counter for each of the blocks, and whenever a block is referenced, the counter is reset to 0 and all other counters associated with the other blocks in the set are incremented by 1. And whenever we want to select a victim, we always scan through all the counters and whichever counter is giving the maximum value, that block will be selected as a victim. So the LRU policy achieves good cache hit rate, but the problem with this policy is as the associativity increases, the maintenance of the overhead due to maintaining this replacement policy increases. If you consider 16-way associative cache, we have to consider 4-bit saturation counter for each of the blocks. Effectively 16 4-bit saturation counters we have to consider, and that is going to incur significant overhead. And also every access we have to update the counter values. To minimize the overhead associated with this LRU replacement policy, we can come up with an approximated LRU policy which is called as a pseudo LRU, pseudo least recently used policy, where rather than considering a log n bit saturation counter for each block, we consider a 1-bit flag, and whenever a block is accessed, the flag will be set and will continue setting the flags of accessed blocks, and once all the blocks in a set having their flag bits set, then we reset all the bits. And whenever we want to select a victim, we either scan from left to right or right to left and select the first block whose flag bit is reset. So this actually incurs only 1 bit of overhead per block compared to log n bit overhead for an n-way set associative cache if you are using an LRU policy. But compared to the pseudo LRU, the LRU policy will achieve better cache hit rate. The current processors, for example Intel, Sandy Bridge and others, so typically use the pseudo LRU policies. There are several variants of pseudo LRU policies and so on. So finally, we are going to discuss the things that related to dealing with the writes in the cache. So when we want to write a particular word to the cache, we can either write the word of data to one level of cache or to the multiple levels of the cache in the hierarchy, So effectively we have two options. If you are writing only to one particular the cache, then that is called as a write back cache, and if you are writing to all the levels of the cache hierarchy, then that is called as the write through policy. Effectively we can design a cache by considering a write through policy or write back policy. So when we consider a write through policy, processor generates, for example, a write request to a particular block. It will be written to the cache as well as it will be written to the lower level of the caches or the memory. In this particular example, we consider two level memory hierarchy where L1 cache and the memory is considered. So whenever we write to a block in the cache, we also write it to the memory. What happens if there is a miss? On a write miss, we have two options. One is we can either write the data directly to the memory, or we allocate the block in the cache from the memory and then write the data to the cache as well as to the memory. So if I consider the first policy, that is the block is not allocated on a cache miss and writing directly to the memory, which is called as write no allocate. The write allocate policy, on a cache miss, first the data is written to the block in the memory, and after writing to the block, the entire block is brought into cache. If there are no reads to the recently written block, then we can always go for write no allocate policy. But if there are multiple reads in the future for a recently written block, then we have to go for write allocate policy. So whether write through policy is efficient or not, remember, for every write you are writing to the lower levels of the memory or the cache, which is effectively takes significant bandwidth requirement, and that is not actually good, especially when we consider a multi-core scenario where multiple cores, when they are trying to write to their caches, they also try to write to the lower level of caches, and there will be a significant bandwidth requirement. And also writing to all the levels of the caches incurs significant energy. So from the energy and the bandwidth point of view, write through caches are not efficient. But the main advantage with the write through caches is it keeps the lower level caches coherent with respect to the higher level caches. So cache coherence maintenance will be simple. The other case is write back. In this, whenever processor is generating a write request, and if the write request is a hit in the cache, it will be written to the block and without writing this data to the memory. Effectively, a cache block absorbs all the write requests from the processor, and this block will be written to the memory only when it is evicted. Since cache block is updated with the processor writes, so it is inconsistent with the memory block. To say that the cache block is updated or inconsistent with respect to the memory, we maintain a one bit of information with the cache block. That bit is called as the dirty bit, and this dirty bit is set whenever processor writes to that particular block. And when the cache replacement policy selects a block as a victim block, and if the block is a dirty, automatically we have to write this dirty block to the memory. On a miss, when a processor generates a request which is a miss in the cache, so when there is a miss, we have to go to the memory and get the block of data and allocate the block or store the block in the cache, and after that we perform our write operations to the cache block. This is similar to write allocate policy of the write through cache that we discussed previously. So obviously, because the write back policy absorbs all processor writes, so it minimizes the bandwidth requirement, and also it minimizes the overall energy consumption by not accessing the memory or the lower level of caches. And it is very attractive for multiprocessor systems. mainly because the bandwidth requirement is not so high. So typically we can consider write through policies mostly at the higher level caches, but for the lower level caches we go for write back caches. So with this I am concluding this module. Thank you.